listen to the random conversations.
Yeah. Well, as I mentioned, I'd gotten ahead of myself through the material. So therefore, I did not go ahead and prepare for the next section because it's just way too soon. The first several homework problems that you have, I mean, the first one that's on paper, then everything else, like the next, like at least 4 problems deal with either finite difference or spectral methods. So really, we should focus on that before getting into anything new and make sure everybody's in good shape on those problems. So so my plan really for this week is just to focus on the homework, and you know, certainly problem 2 has a lot of parts, and in other classes I've had some difficulty with, because I know I have a tendency to ask multi-part questions, but then students don't take the time to fully read the question, and then they'll leave something else, leave something off, and like, well, what can I do? And there's no points for that. And so just to make sure that everybody's able to move forward with these things. So so I guess you could also, you know, think of this as a glorified office hour or something. But and this may not even be the only time we do this, just because there was going to be other homework problems, and I want to make sure that well, I like to make it a priority to iron out whatever issues as far as, you know, what is being asked for, how to do certain things in MATLAB, things like that. So it may not add up to much of a class. I guess it really all depends on how many questions you guys have, and what it takes to get them answered. But this is the golden opportunity to get all these things out in the open.
Can I give my gifts? Is that okay?
What?
Can I give my gifts to people?
Yes.
Hey, that's my bowl.
Yes.
I had fully written that poor little bowl off.
I don't know how many times I've looked at it and said, I need to bring that to Rachel.
Truthfully, I forgot you had that phone charger.
Yeah, I thought you had a duffel bag of like Christmas presents.
If only, but I guess that's what you look around every day.
A little bit longer today, thank you.
Okay. Okay, so the floor is yours.
I have not started the second problem. I've only gotten problem 1 done.
Okay.
I don't like the coding problems, they're hard.
Oh, we're gonna hate the rest of this class then.
I know. I'll be honest, it's because I don't know exactly how to start number 2, nor number 3, nor number 4, nor number 5.
Okay, I appreciate your candor.
4 or 5. There isn't a 4 or 5.
Not on this homework for the rest of the
There's
semester.
homework too.
Oh. Hey.
Yeah, I put up a Canvas, but yeah, I don't think we'll be talking about those anytime soon, but
If I'm being honest, yes, it's because I really don't know how to start it. So
okay.
I'm not exactly sure what to do. Robert was nice enough to explain it to me, but I forgot what he told me. There's a little bit of an issue between my short-term memory coding into the long-term memory.
Evidently, yeah. Okay, well, there's a bit to unpack there. Okay, well, first let's see what anybody else has and see if that helps, and then I
I
can.
know Robert and Samson are much further than that.
Okay.
That's a smart question, guys. I was on 2, but it's been a while since I've been in thesis mode, so.
Oh, well, understandable.
But looking at 3, just right off the bat, I'm not really sure how I'm approaching it, but I haven't actually taken the time to look yet.
Okay.
We don't have to talk about it if you don't want.
Okay. Well, I guess. Okay. Hmm. Oh, you know what? Okay. There's a couple places. So you may have seen, or hopefully you've seen. Oh, you know what? I might not have it in Canvas. Let me see what I have in Canvas. Oh, dang. Whoops. Okay. Well, actually, okay. I need to see what I have under assignments in homework 1. Oh, I do have it. Okay. So as you saw, okay, in either Canvas or my site, when you go to get the problems, there's also the hints file. And I just realized that in the discussion of problem 2 and problem 3, well, first I have a bad reference, so I need to fix that. But I make mention to a MATLAB function that I wrote called diff rule, because so for these problems you need certain finite difference stencils. So the first one that you would need is what we've already seen, just a second order standard difference, where you have like the 1, -2, and 1. But later you need a fourth order rule for a second derivative, and then in problem 3, a 5-point stencil for fourth derivative that's meant to be second order accurate. But I had forgotten to actually make diff rule available. And in the hints document, I mentioned how they're on the lectures page of my Math 460 site, and that may have been true in 2019, the last time I taught this class. Okay, so I should just post those functions in Canvas, just so those are available. Okay. And as far as number 3 is concerned, okay, problem 3, there's not as much going on because you're not asked to do very much, like just write code that solves this problem, and then get the exact solution, which is possible to do by integrating 4 times, and then checking the accuracy of your solution, unlike part 2, where there's part A, part B, and so forth. So problem 3, we have u x x x x is equal to f on the interval 0, 1. And then because this is a fourth order problem in space, fourth derivative, you need 4 boundary conditions. So 4 boundary conditions are u0 is 0, u of 1 is 0, ux of 0 is 0, and ux of 1 is equal to 0. So to get the exact solution, and then the f of x in this problem is given to just be a constant, 24. So what you would do is you would integrate 24 4 times, Now, because you're integrating 4 times, it's going to introduce 4 plus c's, 4 constants of integration. And then you have to take that function that you get from those 4 integrations and plug in x equals 0 and 1 and plug in 0 and 1 into a derivative. And so then you have a system of equations, a system of linear equations in the 4 unknowns, your 4 constants of integration. And that will enable you to get the exact solution. So algebraic pain in the butt, but that's the idea for that part. Now, as far as the matrix, our approximation of UXXXX and XJ is going to be a 5-point stencil. Now, okay. Look at my files here. Okay. Well, how is this? Okay, so what I did was I used my own diff rule to get the coefficients. But instead of simply telling you what the coefficients are, I'm going to have you infer what they should be. If you think in terms of a center difference, so we know center difference rules already for first and second derivative. Okay. And then whoops. Oh. Actually, it is not what I want. Actually, it's only going to be symmetric for even order derivatives. Okay. So here we have forward difference for the first derivative. And then center difference for the second derivative. Over h squared. Now, here, this one is centered, this one is not. Although, I could make it, well, I'd like to have a spacing of just h. Because here, these points are spaced apart by h, with whatever grid spacing you're using. And so are these. If I wanted to make this centered, here's what I could do. I could take a half step in each direction. Uj plus a half minus uj minus a half. Now it's a center difference. So I can put this back and erase. Sorry, you get the impromptu version of me today. And then down below is the spacing between these 2 points. But if I go a half step to the right and half step to the left, that's one full step. So the spacing is again h. All right. So then what I could do is I could continue this pattern. And by the time I get to fourth derivative, anytime I have an even order derivative, then everything works out nicely as far as centering everything. So u x x x x of xj will be some coefficients over h to the fourth. And here I'm using 2 points, here I'm using 3 points, and so on. So if you look at how many points are used and where they're placed, and also the coefficients of the points, then what you can do is generalize from these cases to get the coefficients here, which would agree with what you would get from running diff rule. So based on the pattern that you see started here, what do you think the coefficients will be down here? Or how would you figure them out?
I feel like it's 1, 3, 6, 3, 1.
Almost.
Would it be 1, 4, 6, 1?
4. Yeah, so third derivative is 1, 3, 3, 1.
Yeah,
And it's 1, 4, 6 for 1. So yeah. So yeah, it would be uj plus 2 minus 4 uj plus 1 plus 6 minus 4 plus 1. So that's what diff rule would give you if you ran it. So that's your stencil for the fourth derivative. And all of these are second order accurate. Because now, normally, if you're approximating the nth derivative with only n plus 1 points, that would normally be only first order accurate because it's the minimum number of points that you need. But because of symmetry, you get an extra degree of accuracy. So it all gives you second order. Okay. So now you have that. But then, to solve this PDE, you want to set up a system of equations of a form AU equals F, where F is the vector F is going to consist of the values of F plus any boundary terms. Although in this case, you're not going to have any boundary terms for this problem. Generally you would. This time you won't. Can anyone tell me why? Yeah, the boundary values are 0. Homogeneous boundary conditions. So you won't have boundary terms to add. So your right-hand side vector is going to be a bunch of 24s. Okay. All right. And then for the matrix, we have 1 over h to the 4th on the outside. So for the most part, if we forget about the boundary conditions for the time being, what should we see in, I guess, most rows of a matrix? Based on these coefficients here. You might we've seen a number of examples involving a second derivative and what kind of matrix we got from this center difference rule.
Wouldn't it just be the coefficients from UX around the diagonal?
Yes, it would be. So for instance, you'd have 6 down the diagonal, then minus 4, and 1, and then that's most of it. So it would be a pentadiagonal matrix instead of like tridiagonal that we've seen with the second derivative. But we have to think about the boundary conditions So if you look at our spatial domain, 0 to 1, so we have a spacing 1 over n plus 1 is h. This is x1, x2, x3, and so on. Okay. And so uniform spacing between all the points. So, actually, the easier case to consider is the, like for instance, the second row. Okay, so I'll fill it in -4, 6, -4, and 1. So the second row is going to involve, this is U2 on the diagonal, so U1, U2, U3, U4. So when J is equal to 2, so we have U4, U3, U2, U1, and U0. But what's U0?
0.
It's 0 because of this boundary condition. And similar for the second to last row. So in fact, we don't need to do anything here. This row is fine the way it is. One point that's left off in the stencil is its value is 0 anyway. So, okay. So then there's a matter of what about the first and last rows, where you have to account for not just u being 0, but ux being 0. Because here we have u3, u2, u1, but then you have u0, and then u sub -1. So we need a way to account for that. So if we look more closely at what's happening near the left boundary, then we can figure out how to account for both boundary conditions on the left side. Okay, so the UFX x at x1 is, okay, so we have u3 minus 4 u2 plus 6 u1 minus 4, whoops, I forgot the u here, u0 plus u sub -1 all over h squared. Now, we know that's 0 because of...
Why is it h squared?
Oh, no, it should be h to the 4th. I think it's usually doing second derivative, but have it run at h squared. Thank you for catching that. Okay. So that's gone. But then what about this? So for that, we consider, we need a way of approximating the first derivative at this point that's going to involve this point. So our approximation of ux at x naught, which we know is equal to 0, so what would be a good approximation to use? Because there's more than one choice. So you're approximating a derivative here using nearby points, but we want to include this one.
u0 minus u negative 1 over h.
Okay, so u0 minus 1 over h. Okay, now if you do that, so you test this equal to 0. You know that this already is 0. Therefore, you conclude that this is 0 also. Now, Unfortunately, there's one problem with using this finite difference rule, because we're using it to approximate the derivative at x0 and using this point to help us. So in terms of a basic finite difference formulas for first derivative, we have forward difference, backward difference, center difference. Which one is this? It's not forward.
Go backwards.
It's backward difference because it's approximating a derivative at this point using a point to the left. So this is a backward difference. Okay. What's the order of accuracy of a backward difference? Yeah, order H. It's first order accurate. What does the second order accurate? So it would taint the accuracy of the overall solution to use a first order accurate difference. So what should we use instead?
Center difference.
Center difference, and what would that look like?
That will be U1 minus U negative 1 over H. Yeah.
Not H.
H squared.
No, not H squared.
Or 2H.
2H.
Yeah.
Okay. So center difference. So make sure that whatever finite difference formula you're using to approximate derivatives of at the boundary is the same order of accuracy, at least, as the whatever finite difference formulas you're using in the interior. Okay. All right. So now you can express u sub minus 1. So you solve for u1, and then you incorporate that in here. So what that's going to do is, since u sub minus 1 will be expressed in terms of u1, and keep in mind this whole thing's supposed to be equal to 0 because of a boundary condition, it's going to change the coefficient of u1. So that's going to change by enforcing a boundary condition. Same thing's going to happen down here. What?
Are we recording this?
I believe I was. Yes, I'm recording this. I sense some urgency there. All right. Okay. So then your matrix will be in order to enforce everything. Then you're ready to solve the system and plot your computed solution against the exact. So it's watching boundary conditions that are the pain here.
So, I was gonna ask, I'm curious, like, how does different give us, because different gives us the matrix, or
Oh, sorry, what?
the different?
The diff rule function, what it does is you specify what is to get the coefficients of a finite difference rule. So the way you would call it for this problem would be like a first argument would be like the indices -2 to 2 because you're using points, j minus 2 all the way up to j plus 2. And then the second argument is the order of derivative that you want, which would be 4 in this case, and it would spit out these coefficients. But I figure since I get to show you these lower order rules and get you to extrapolate down to here, that you can get it that way. So now you don't need diff rule for this problem. Although you still would want it for problem 2 that requires a fourth order accurate formula for the second derivative. But yeah, so I'll be sure to post that. Okay, so any questions about what happened here? What do you think about the first derivative is, so here this is center difference. Here for u0, for x0, it is a forward difference, but this same rule is a center difference from a point that's halfway between these two. That'd be u sub minus 1/2. But it's because we needed the derivative at this point. This point has to be in the middle. Okay. One other comment I want to make about the first part of this, where you're integrating this 4 times to get the exact solution. Once you have the equation, like if you're working this out on paper, for instance, and you're writing out your formula for the exact solution, for constant integration, and then you plug in x is 0 and x is 1, and for u and ux to get your 4 equations and 4 unknowns. Well, at least one of those equations will probably be very simple and reveal one of a constant right away. But once you have a system of equations, what you could try doing is just go ahead and setting up in MATLAB, like the coefficients of your arbitrary constants forms a matrix, and then your right-hand side values would that would form your B. So you're setting up an AX equals B problem, and just go ahead and have MATLAB solve it for you. What I would recommend, though, for doing that is because in this case the coefficients will work out pretty nicely, like fractions. If you do okay, so solve your constant integration, which I'll call C1, C2, C3, C4, with backslash in MATLAB. I would recommend doing format rat for rational. So that way, when you solve the system using backslash, it'll display the solution as fractions. Instead of having to, I mean, you're going to put these into your code to implement the exact solution for checking your error. And so instead of having to type in a zillion decimal places, you just have a fraction and have it exact. Questions? I wasn't sure how much I'd have to talk about today, but it's working out pretty well. Okay. Now, there's one more generic thing I want to talk about. This actually applies for both problems 2 and 3. And it's like, once you have a computed solution, and in both problems you have an exact solution, how do you check order of accuracy? Like, if you expect it to be second order accurate or fourth order accurate, how do you verify that? Either computationally or visually. Okay. Both problems 2 and 3. Okay. So, what you need is, at least for visualizing your error, you need these vectors of your steps, your spacing h, and the error. So like if you take the norm of a difference between your computed solution and the exact solution on a grid of a certain size with a certain spacing h, then you have, like I say, if you carry it out for 3 different spacings h, then so you have a vector of 3 h values and corresponding errors. Now, for both of these problems, it's Dirichlet boundary conditions, so the grid spacing is also on a domain 0 to 1. So this is domain 0 to 1, Dirichlet boundary conditions. Well, okay, problem 3 has both Dirichlet and Neumann because conditions on U and UX. But the point is, because U is specified on the boundary, your unknowns are just the points in the interior. Okay. So what I would suggest, just as a convenience for this problem, is you set your number of grid points n equal to some power of 2 minus 1. So that way, your grid spacing h will be a negative power of 2. So that way you'd have, like if you choose n based on consecutive powers of 2, then you'd be cutting h in half, and then in half again. All right. Now, if the method that you're using to solve the PDE has some known order of accuracy, h to the p, then if you cut the step size in half, causes the error degree decrease by a factor of 2 to the p. So you follow this path for choosing a number of grid points. So you end up having spacings h, some h, and then h over 2. Then you should see the error decrease by a factor of 4 for a second order method. So if you just look at the numbers, you can check that to see if you're getting the order of accuracy you need. But what else you can do is, of course, plot it. So use a log plot of your vector of h's and your vector of errors. So what will happen is, since the error is supposed to be order h to the p, it's supposed to be a line on the plot that has a slope of p. And to see that, if the error satisfies this, now this is not going to be exact, but it should be approximately this, then log of the error would be equal to log of c, that's an unknown constant, plus p times the log of h. So we see here, y equals mx plus b. So it really is an equation of a line. In fact, I'll even label that. Y equals mx plus b. on a log plot, because of a rather freaky axis scales they use, it can be difficult to infer slope. I mean, you'll see it's a line, but it's difficult to judge that it has the right slope. So what you can do to visually check the slope is plot a second line. Plot h versus h to the p. Also puts a dot in there because it's a vector, where p is the expected, like a theoretically expected order of accuracy. So then if your method really is order h to the p accurate, p4 accurate, the line should be parallel. Oh, use a different color, like red for this, and blue is the default, but anyway. Different colors, so you can keep track of which is which. Okay, so that's how you can visually inspect order of accuracy. For problem 2, I would not recommend using a small number of grid points because the exact solution is a rather oscillatory function. When a function is rapidly oscillating, it takes more grid points to represent it accurately. So what will be happening is if you use a small number of grid points, your method might be correct, and you graph your computed solution, the exact solution, and they might still seem off even though really they aren't. So that's one thing to keep in mind to check your method. Okay. So questions about this? Okay. Or anything else for that matter? Let's say even if we just focus on problems 2 and 3.
So for 2B, it's only because we haven't seen the function. I'm not sure how we said we use diff rule and self-found with Lagrange.
Oh, because diff rule, depending on which version of it, uses make Lagrange.
So the diff rule uses Lagrange.
I think I have different versions of diff rule that compute the coefficients in different ways.
I have some of the, which one? I have them with Lagrange function.
Okay.
Yeah, sure.
Yeah. So when I post it, I'll post whichever is needed because one way of getting the coefficients is to compute the Lagrange polynomials and then take the appropriate derivative of them and evaluate it at the point. And the other way is setting up a AX equals B system. And I think I have diff rules that do both things. So, so if a version of diff rule I'm posting needs make Lagrange, then I'll post make Lagrange. Okay, yeah. So for this problem or part of the problem, you need different stencils for the boundary versus the interior. And that's to get high enough order of accuracy. And because with second derivative, a 3-point centered stencil is second order accurate. So to get fourth order accuracy, you need 2 more points for a total of 5. But then at the boundary, you can't use a centered stencil because you have points that are falling off the edge. So you need So your rule is not centered anymore. Therefore, you need 6 points instead of 5.
The reason why I'm asking is the make rule I have, that you posted a long time ago on this class,
Uh-huh.
computes coefficients of finite difference approximation of f prime. Just the
Oh, okay. Yeah. So I have another version that takes the order of derivative as an input. Yeah. Yeah, because I think I'd assigned a diff rule for like 460 or 560 that is only about the first derivative. So that won't help here. Okay. All right, so I guess I better hurry up and get that stuff in Canvas. Okay. We'll still have some time. Anything more? Well, I'm fine with calling it a day. Especially since I have 2 more classes after this one. Well, I guess, Caitlin, I'll see you in 45 minutes. Okay, and recording is stopped.